This is the final video for Further Kinematics, and in this video we're going to look again at variable acceleration in 2 dimensions. But this time we're going to look at changing acceleration to velocity and velocity to displacement, and we do that by integration. If you remember the previous video, we were differentiating, so we went from displacement to velocity and velocity to acceleration. Okay, now remember, when we integrate we need a constant of integration, but when we integrate vectors, because it has 2 components, we need 2 constants in component form. Okay, and again we can use boundary conditions to find the values of those constants. So let's have a look at this first question, and this is example 15. And it says a particle is moving in a plane. Now you can think of a plane as just a flat surface that you're looking down on. At time t seconds, the velocity is given by, v equals, and it's 3t I plus a half t squared j. So let's have a look what we've been required to do. So we're told that when t equals 0, the position vector of p with respect to a fixed origin is 2i minus 3j. Those are our boundary conditions, so we're going to use those to find our constants of integration. And it asked us to find the position vector of p at any time t. So the first thing we're going to do is think, well, we've been given velocity, I won't get back to position vector, so we're going to integrate. So we get r equals, so if you integrate 3t with respect to t, you get 3 over 2t squared, and that's in the I direction. And if you integrate a half t squared with respect to t, you get a 6 of t cubed in the j direction. And again, we're going to just add on our pi plus qj. Now you don't have to use p and q, you can use c and d, you can use anything you like. Right, now we're told when t equals 0, r is 2i minus 3j. So remember what we're going to do there. Okay, when t is 0, so we're going to put 0 in here. Okay, so therefore the left hand side is 2i minus 3j. If we substitute t equals 0, we're just left with pi plus qj. Okay, and therefore you can see, therefore p must equal 2, q must equal -3. And then we just update our position vector, our general position vector. So r equals 3 over 2 t squared I plus a 6 t cubed j plus 2i minus 3j. What we usually do is we pull the i's and j's together. So we're just going to do that. So it's 3 over 2t squared minus 2, and that's your I component, and then got a 6 t cubed minus 3j, and that of course will be meters. Okay, right, so let's have a little look at the next example. This is example 16. So it says a particle p is moving in a plane so that at time t seconds its acceleration, now let's have a look, its acceleration is 4i minus 2tj. Now notice that's variable because it's got t in it. The minute you say variable acceleration, you cannot use that. Okay, we're told that when t is 3, the velocity is 6i, and when t is 3, we know the position is 20i plus 3j. Okay, so the first thing we're asked to do is find the angle between the direction of motion. Now, direction of motion is always when we're moving, so we need the velocity, and the I, which remember is horizontal, okay, when t is 2. Okay, so let's have a look at what we've got. Now we've been given A is 4I minus 2tj, therefore the velocity, so we're going to integrate it, and this time I'm going to put my constants of integration in as I'm doing it. So I'm going to get 4t plus p, the I, plus, and then it's minus t squared. Remember, when you integrate minus 2t, you get minus t squared, plus q j, and that's in meters per second. Okay, now we know when t equals 3, we were told that the velocity was, now very carefully, it was 6I plus no j. And I always tend to put that in just so that I'm careful. Right, so therefore 6I plus 0j equals, and I'm going to put t in. So if I put t as 3 in, I get 12 plus p in the I direction, plus, and then if I put 3 in, minus 9 plus q in the j direction. What I'm now going to do is a bit of comparison. Okay, so the first thing I'm going to do is I'm going to look at the eyes, and I will highlight those, choose a different colour. So on the left hand side we've got 6I, and on the right hand side we've got 12 plus p I. So therefore I can say 6 must equal 12 plus p, therefore p must equal negative 6. And then if I look at the j's, and again I'm just going to highlight those. Okay, on the left hand side we've got no j, and on the right hand side we've got minus 9 plus q. I'll write that down. Therefore 0 equals negative 9 plus q, therefore q must equal 9. Let's put those back in. So therefore p must equal, that's 4t minus 6 in the I, plus it's minus t squared plus 9j. Okay, and that's again meters per second. But the question says, remember, that is the general velocity vector. So I want the angle between the direction of motion of p and I when t is 2. So when t is 2, I put t as 2 in, I get 2i plus 5j. All I've done, okay, is substituted t as 2. Okay, now I want the direction of motion, so I'm just going to draw a little diagram of that velocity. So it goes across 2 and up 5, and it said, okay, and I, remember I is 1 in the x direction. Okay, so it's in that direction. So what I want is I want this angle. Okay, so it's going to be basic trigonometry. So alpha equals tan to the minus 1 of opposite over adjacent. So alpha is 68.2 degrees, and that's to 3 significant figures. So that is the angle between the direction of motion of p and I when t is 2. Okay, now the next thing it asks us for, if you look, is the distance of p. The distance of p from the origin when t is 0. So let's have a little look at this one. So the first thing we're going to do is we're going to take our velocity vector, and here it is in part A. Just highlight it, there it is. Okay, there it is. Oops. Okay. and we're going to integrate that again. But if you remember, in the original, we were told a piece of information about the position when t was 3. Okay, so our position, we're going to integrate, so we get 2t squared minus 6t plus m. Now, notice I'm using a different letter. I'm not using p and q. I'm going for m and n. Again, if we integrate, minus a third t cubed plus 9t plus n in the j direction. So all I've done is I've integrated both components of my velocity and added on a new constant for the I and a constant for the j. Now, in the question we're told when t is 3, r was 20I plus 3j. So we're going to pop those in. So therefore, 20I plus 3j equals, and again, I'm going to substitute 3 in wherever I see t. Okay, and this time I'm going to short that. So I'm going to get 2 lots of 3 squared minus 6 lots of 3 plus m in the I direction plus, and it's minus a third 3 cubed plus 9 lots of 3 plus n and j. Just going to sort that out, so we get 20I plus 3j equals, and you end up with m in the I direction plus, and then it's 18 plus n in the j. And we're going to do what we did before. We're going to do a bit of comparison, so we're going to compare the i's. So on the left hand side you've got 20, on the right hand side you've got m. Okay, so you can say 20 equals m. And again, if we just do the j's, and I'll do it here. Okay, use a different coloured highlighter. You can see that 3 equals 18 plus n. Therefore, oops, underneath, n equals negative 15. So therefore, r equals, so it's 2t squared minus 6t plus 20 in the I direction, and negative a third t cubed plus 9t minus 15 in the j. Now we want the distance of p from the origin when t equals 0. So when t equals 0, r will equal 20I minus 15j, but it actually asks us for distance. Okay, so we're going to use Pythagoras. So the length of O to P is the square root of 20 squared is negative 15 all squared, which is 25 metres. Okay. Right, so we'll just look at our final question now, and this is example 17. And these are examiners' favourites. Okay, so the first thing it says is the velocity of a particle p at time t seconds is given to us by this velocity vector. Okay, so you've got 3t squared minus 8I plus 5j metres per second. When t equals 0, the position of p with respect to a fixed origin is 2I minus 4j. So we want to find the position vector of p after t seconds. Okay. So the first thing we're going to do is we're going to start and we're going to find r. So we've got r equals, and again we're going to integrate. Okay. Sorry, what I'll do is I'll start with, I will write my v. So I'll just rub that out. So write down what v is. So v equals, so it's 3t squared minus 8I plus 5j. Therefore, r must equal, if you integrate that, you get t cubed minus 8t plus, I'm going to go for c, I plus, and it's 5t plus dj. And we're told when t equals 0, r is 2i minus 4j. This should beginning to start being very samey. So therefore 2i minus 4j equals ci plus dj. So you put t as 0, any term with t disappears. Okay, you can see from that c is 2 and d is negative 4. So therefore, rp is t cubed minus 8t plus 2 in the I and 5t minus 4j. Okay, right, so the last little bit, and again examiners do like this, it says a second particle q moves with a constant velocity. Okay, that's quite important, it's a constant velocity. Okay, 8i plus 4j. When t equals 0, the position vector of q with respect to a fixed origin is 2i. Okay. Now, if you remember in one of our previous videos, okay, we talked about using some of the other formulae, and one of them is I can write RQ as R0, which is its in original position plus velocity times time. Okay, now I know that its initial position is 2i, so therefore RQ equals 2i plus, now it's travelling with a velocity 8i plus 4j, and that's t. Okay. Now I can write that RQ, so this is the position of q relative to an origin, is going to be 2 plus 8ti plus 4tj. Now, the question set prove that P and Q collide. Now, if P and Q collide, so right here, if they collide, then RP must equal RQ. So let's just have a little look. So we're just going to go back and I'll show you RP. There it is at the top of the screen. So we're just going to look at the I components and the J components. Okay, so we'll look at the I's first. So we're going to compare the I's for the two things, for RP and RQ. Now if you look above you can see, therefore we'll look at the I's. So t cubed minus 8t plus 2 must equal 2 plus 8t. That's the I's. Now, if we start to solve that, we get t cubed minus 16t equals 0. We're going to solve that. Okay, so I'm going to apply t as a common factor, so I get t squared minus 16 equals 0. So I get 3 possible t values. T equals 0, t equals negative 4, t equals positive 4. Well, one of those I'm going to reject. This one I'm going to reject, and I'm going to state why I'm rejecting it, because t has to be greater than or equal to 0. Okay, now that I've only just compared the i's. Now what I'm going to do is then compare the j's and see if I get a corresponding t value. So on this side I'm just going to do the j's. Okay, again, if you look at P, you can see the j component was 5t minus 4. 5t minus 4. And I'm going to set that equal to the j component for RQ. That's 4t. If you rearrange that, you get t equals 4. And you should now be able to see that for both the i's and j's, we've got the same time. So when t equals 4, the i's and the j's are the same. So that means that they collide when t equals 4. All right, well, we just need a little conclusion. So I'm going to write as t equals 4 satisfies, oops, spell now, oops, it satisfies, okay, both equations, okay, then the particles collide when t equals 4. Right, and that is the end of this video for further kinematics.